All right, let's jump right into it. Welcome to this explainer, where we're going to break down the fundamental structure of the atom. We're embarking on this really fascinating journey straight into the core of all matter, because honestly, understanding the atom is pretty much the key to understanding the entire universe.
So let's kick things off by completely shrinking down to the microscopic level. Just imagine, for a second, if we could actually scale ourselves down and explore this invisible world, kind of floating right alongside these complex molecular structures. I know it sounds like straight-up science fiction, but this microscopic realm is the absolute reality of the world we live in every single day.
And here's the crucial point, the big takeaway to keep in mind. Literally everything in the universe is made of atoms. Whether we're talking about the green leaf right outside your window, a massive burning star light years away, or, you and me. Every single physical thing is constructed from these unbelievably tiny building blocks.
Here is how we're going to unpack this today. We'll start with the journey to the microscopic, move right into matter's heart, the nucleus, then see how an atom is actually built. After that, we'll explore those electron shells orbiting the core and wrap up by looking at isotopes with the carbon family.
Okay, Section 1. Journey to the microscopic. Entering the quantum world.
When we picture an atom suspended in space with that dense central nucleus surrounded by these energetic, orbiting rings of electrons, it's a pretty beautiful parallel, right? The microscopic structure actually closely mirrors our macroscopic solar system. But here's a fun fact to put things into perspective. If an atom were the size of a massive sports stadium, the nucleus would just be this tiny little pea sitting right on the 50-yard line. So wild as it sounds, most of the atom is actually completely empty space.
Moving on to Section 2. The nucleus, matter's heart, specifically protons and neutrons.
Now, we can really visualize this heart in two distinct ways. Conceptually, it's easy to think of it as this friendly little bundle of positive protons and neutral neutrons. But in reality, it's a highly dense, tightly bound cluster of subatomic particles, all locked together by these incredibly strong nuclear forces. It's intense.
To really build our foundation for how this core works, we need to quickly define who actually lives there. First up is the proton. Just remember that the proton carries a positive charge. But honestly, more importantly than that, the number of protons acts as the ultimate unique identifier for any given element. If you change the number of protons, you literally change what the element is. It's a total identity shift.
Next up, we have the neutron. And the neutron, as the name cleverly suggests, is entirely neutral, so it brings zero electrical charge to the table. But don't let that fool you. It is absolutely vital for two huge reasons. It gives the atom its mass, and it acts almost like a molecular glue. It provides the necessary stability to hold those repelling, positively charged protons tightly together in that dense nucleus.
And finally, orbiting way out far from that dense nucleus, we have the electron. This is a tiny, incredibly fast-moving subatomic particle carrying a negative charge. It perfectly balances out the positive charge of those protons in the center, and it travels along very distinct pathways, which we call shells, right around the core.
All right, Section 3. Assembly. Building an atom. Putting the pieces together.
Let's look at this like a sort of metaphorical particle assembly line. Imagine exactly how loose subatomic particles, your red protons and blue neutrons, are sourced, beamed through a counting machine, and then finally combined to form a stable atomic nucleus. Let's break down exactly what that process looks like.
So, the whole assembly process happens in three really clear, logical steps. Step 1, we gather up the loose positive protons and neutral neutrons. Step 2, we pass them through this identification and counting zone, just ensuring we have the exact right mix for what we want to build. And step 3 is the final nucleus assembly, where those particles are tightly bound together to give us our total nucleon count. So, applying that exact math to the atom we just assembled, taking exactly 6 protons and adding 6 neutrons gives us a total mass number of 12 nucleons. And this specific recipe creates a perfectly stable carbon-12 nucleus. It's pretty cool, right? If the recipe was even slightly different, the end product would be a totally different thing.
Section 4. Orbiting the core. Electron shells, the Bohr-Rutherford model.
Now, the classic Bohr-Rutherford model clearly charts out the concentric paths that these electrons take around the core. And what's really important to notice here is how it isn't just a random, chaotic cloud. These paths are structured into very specific, mathematically precise energy layers radiating outward from that nucleus.
And we designate these specific layers by letters, the K, L,
M and N shells. The K shell is the innermost one, the one closest to the nucleus, representing energy level 1. Then we step outward to L, M, and N. And here's the kicker. Each of these specific rings is capable of holding a certain, strict maximum number of negatively charged electrons. They always populate from the inside out, perfectly balancing the atom's charge.
Which brings us to Section 5, Isotopes, the carbon family. Let's look at atoms with different neutron numbers.
So what happens if we mess with that recipe we talked about earlier? This brings us to a crucial definition. Isotopes are basically variations of the exact same element. Because they have the same number of protons, their actual elemental identity doesn't change at all. However, they carry a different neutron payload, which means they have different mass numbers. Let's look at how this physical payload difference actually plays out.
When we look at the carbon family side by side, that's carbon 12, 13, and 14, you can trace exactly how the addition of just 1 or 2 extra neutrons visibly alters the nucleus, even while those outer electron shells remain completely identical.
Breaking down the data, it's pretty revealing. All 3 variations possess exactly 6 protons, which keeps them officially categorized as carbon. But that 7th or 8th neutron steadily increases the total mass number, and more importantly, check out the drastic shift in stability. While carbon 12 and 13 are nice and stable, adding that extra weight makes carbon 14 unstable and actually radioactive.
Let's quickly zoom in on carbon 14 to understand why this actually matters in the real world. Because carbon 14 has those 2 extra neutrons, creating a physical imbalance, it's unstable. So over time, it undergoes this process called beta decay to try and reach stability. And the amazing part is, it does this completely predictably with a very precise half-life of 5,730 years. This measurable, steady decay is exactly what makes carbon-14 the absolute perfect, highly accurate tool for radiocarbon dating used by scientists all over the globe.
So ultimately, the structure of the atom isn't just magic. It's this beautiful, delicate, and mathematically precise balance of protons, neutrons, and electrons all working together in perfect harmony.
As we wrap up this explainer, I just want you to take a moment to ponder the amazingly complex, elegant machinery that is operating inside every single invisible speck of matter around you. It really begs the question, what other secrets are hiding right there inside the universe's tiniest building blocks? Thank you so much for learning with me today.